The paper addresses the challenges of applying deep learning techniques in manufacturing for defect detection, particularly due to the scarcity and imbalance of training data. It proposes a novel domain adaptation approach that leverages knowledge from an existing source dataset to address these issues. This approach combines domain adaptation with an autoencoder-based data augmentation method to improve performance on imbalanced target datasets. The proposed method is evaluated using image data for wafer defect prediction and shows superior performance compared to other algorithms when dealing with limited and imbalanced labeled samples in the target dataset. In the context of wafer manufacturing, scarce and imbalanced datasets pose significant challenges. To address these issues, a novel pipeline is proposed, combining autoencoder-based data augmentation with domain adaptation. The autoencoder generates synthetic data for minority classes by leveraging Gaussian noise and the latent space, effectively mitigating the problem of imbalanced data. This approach enables the creation of additional data points that are similar to the minority class, thus reducing the class imbalance. The domain adaptation component is built upon adversarial learning, designed to adapt to heterogeneous source and target datasets. This allows the pipeline to effectively handle domain shifts between the source and target datasets, ensuring improved performance. The proposed pipeline is evaluated on commonly used wafer manufacturing datasets, demonstrating superior performance when both methods are used in conjunction, compared to utilizing each method individually. This integrated approach effectively addresses the symptorial problem by generating synthetic data that can bridge the distribution gap between synthetic and real-world data. By leveraging the strengths of both autoencoder-based data augmentation and domain adaptation, the proposed pipeline offers a robust solution for wafer manufacturing datasets, where data scarcity and imbalance are prevalent. This innovative approach has significant implications for improving the accuracy and reliability of wafer manufacturing processes. The proposed domain adaptation method consists of two primary steps. First, a balanced target dataset is generated by augmenting limited target data with synthetic data using an undercomplete autoencoder. This autoencoder is trained on the target data to learn a compressed latent space representation, which is then used to generate new synthetic data by adding random noise and passing it through the decoder. This process is repeated for classes with limited samples to obtain a balanced dataset. The second step involves training a classification model using an adversarial domain adaptation approach. The architecture consists of 5 neural networks, private generators for the source and target domains, a shared generator, a discriminator, and a classifier. The private generators learn domain-specific representations, which are then passed through the shared generator to learn a domain-independent latent space representation. The discriminator is trained to distinguish between the source and target domains, while the classifier is trained to predict labels for both domains. The loss functions for the classification and discriminator networks are defined as LC and LD, respectively. LC measures the error of label prediction in both domains, while LD measures the domain classification error. A penalty coefficient lambda is used to balance the loss values obtained from the source and target data points. The goal is to minimize both LC and LD to obtain a good classifier and discriminator. This adversarial domain adaptation approach is illustrated in Figure 1, which shows the architecture of the algorithm. The source and target data are fed into the private generators, producing domain-specific representations. These representations are then passed through the shared generator to obtain a domain-independent latent space representation. The discriminator and classifier networks take this representation as input to produce the domain identity and label predictions, respectively. Training adversarial generators against a discriminator necessitates minimizing generator loss to achieve domain invariance and predictive information in domain-independent representations. This process involves optimizing both generator loss and classification loss, where the discriminator is trained to maximize domain classification accuracy. The learning process employs a mini-batch gradient descent procedure. The training algorithm consists of 3 primary steps: training the generators, training the classifier, and training the discriminator. In the generator training step, the generator loss is minimized to produce domain invariant representations. The classifier is trained on labeled data from the source domain to predict the defect labels. The discriminator is trained to distinguish between the source and target domains, with its loss minimized to ensure domain invariance. The experiment focuses on wafer defect prediction, utilizing the mixed WM381 dataset as the source and the WM811K dataset as the target. To address common manufacturing dataset challenges, such as in-labeled samples and imbalanced data, data augmentation and class balancing techniques are employed. Data augmentation involves applying random transformations to the images, while class balancing ensures equal representation of defect and non-defect classes. By optimizing the generator loss and incorporating these techniques, the model achieves improved performance in wafer defect prediction, demonstrating the effectiveness of the proposed approach in addressing domain shift and class imbalance issues. The research discusses various approaches for training domain adaptation (DA) models, including adversarial DA with and without data augmentation, fine-tuning a pre-trained VGG16 model, and training a vanilla deep neural network. These approaches differ in the type of target training data used, with some using augmented data and others using imbalanced data. The goal is to evaluate the impact of target training data size on performance. The DA models are trained using TensorFlow and Keras libraries, with specific hyperparameters for each approach. The results, presented in Fig. 2, show the classification precision scores for each approach with varying target data sizes. When evaluating the performance of various models on the WM811K testing data, a focus on balanced classification accuracy and precision reveals notable differences. The adversarial DA approach, augmented with target data, outperforms both fine-tuning and vanilla classifier methods across diverse sample sizes. Notably, incorporating augmented target data into training yields significant performance gains. Specifically, the adversarial DA approach exhibits a 5% to 16% increase in balanced accuracy and a 6% to 15% increase in precision when utilizing 1,000 augmented target samples. In contrast, fine-tuning struggles to learn effectively with imbalanced target data, underscoring the adversarial DA approach's superior generalizability on target test data. Furthermore, recent advancements in transfer optimization and reinforcement learning have paved the way for extending the DA approach to non-classification tasks, opening up new avenues for exploration. This novel adversarial domain adaptation approach supports heterogeneous adaptation, where source and target domains have different features. The method employs two private generators and one shared generator to extract features predictive of target labels while being uninformative about the domain. This design addresses the scarcity of target training data, a common issue in manufacturing settings. To augment minority classes in the training data, an autoencoder-based technique is applied, followed by the domain adaptation process. Experimental evaluation on wafer defect datasets demonstrates superior performance compared to other baseline approaches. The approach is situated within the context of related works on deep learning, generative adversarial networks, and reinforcement learning. It highlights the challenges of domain shift in learning-based robotic perception and control, as well as the need for domain adaptation in reinforcement learning to ensure effectiveness even when input distributions change over time. Notably, the approach requires at least some labeled data from each class in the target domain, and its performance could be improved by using data from multiple related domains. Future research directions include addressing the symptorial gap in robotic perception and control. The proposed approach has potential applications in improving zero-shot transfer in reinforcement learning and enhancing the performance of neural audio synthesis models. This work is funded by NSF under grant CMMI 2,134,667, focusing on privacy-preserving tiny machine learning edge analytics to enable AI commons for secure manufacturing. I apologize, but it seems that the original text is incomplete. Please provide the complete text, and I'll be happy to refine it according to the guidelines. I'll transform the text into a direct, concise form suitable for voiceover narration, maintaining technical accuracy and depth while explaining key terms, concepts, and methodologies with precision and clarity.